Welcome to the BMP RAM user guidance video series. Each of these videos is designed to be 10 to 15 minutes long and provide supplemental information to the BMP RAM user guidance document available for download at bmpram.com. This video, entitled Generating BMP Inventory Data, guides you through the general concepts and steps to locate, inventory, and populate essential data for structural BMPs and BMP RAM. Additional videos in this series will discuss setting benchmark and threshold values, collecting field observation data, and viewing and tracking BMP RAM scores over time. A structural BMP is a physical structure that has been specifically sized to accept, attenuate, and/or treat urban stormwater runoff through some combination of detention, retention, or filtration. Structural BMPs are implemented on public and private property to improve downstream water quality by either reducing runoff volumes and/or capturing pollutants and reducing the associated concentrations. In most instances, structural BMP sizing is based on site considerations to treat regional stormwater volumes generated from the contributing urban drainage area, such as the 85th percentile 24-hour precipitation event or 20-year 1-hour storm. Other guidance videos are available in this series that discuss how to correctly identify and distinguish the various types of centralized and decentralized structural BMPs. The purpose of the inventory step in BMP RAM is to locate each BMP on the map, assign a unique ID, determine and record the BMP type, and document information that is important to establishing scoring equations to quantify and track BMP effectiveness over time. The BMP-specific design parameters are also used by our Urban Stormwater Pollutant Loading Model, TELR, to translate BMP RAM results into estimates of average annual stormwater volume and pollutant load reductions to the receiving water. We realize that when users are inventorying existing structural BMPs, obtaining some of the inventory data may require some time. However, inventorying new structural BMPs at time of construction should be easy given that most of the information and specifications necessary for BMP RAM are also required for construction. All users should remember that each BMP is inventoried only once, and this information should not change over time. The inventory information for each structural BMP includes location, BMP type, drainage area, the number of inlets and outlets, and a few design parameters specific to each BMP type. Users are also able to enter any pertinent notes as desired. The necessary inventory information will be obtained through a combination of field inspections and office work, and this balance will depend on the amount of as-built design information available to the user for each structural BMP. In addition to field observations, users are encouraged to utilize any available design and engineering plans for the BMP, as well as GIS and/or Google Earth. The rest of this video walks you through the inventory steps and provides guidance on design parameters required by BMP RAM and potential ways users can obtain these values. After clicking on the Inventory button in BMP RAM website or app, there are two options in the lower right-hand corner: Add New BMP or Bulk Upload Many BMPs. This video goes through the steps for inventorying a single BMP. Users who would like to bulk upload existing structural BMP inventory data into BMP RAM should refer to the BMP RAM user guidance document for details on how this is done. To add a new BMP, manually select Add a BMP. Next, navigate on the map to find the BMP location and click to place the BMP marker. Latin long coordinates for that BMP are recorded. For the most accurate placement, we recommend that you access BMP RAM through a mobile device and stand on or within the subject BMP during this process using the blue dot generated by your device's internal GPS. In the General Information Attribute window, you are asked to give your BMP a unique BMP ID. This ID should be simple, no more than 20 characters, easy to remember, and must be unique within your data management system. We recommend all municipalities devise their own structural BMP naming convention to make naming of future BMPs straightforward. In this example, we'll call our BMP Watt to signify we're looking at Watsonville, DB1 to give it a unique alphanumeric identifier which is meaningful to its BMP type, and 2016 to denote that we're inventorying it in 2016. You should use a naming convention that makes the most sense for your municipality and your network of BMPs. The next data field is BMP type. In this example, we'll select dry basin. Refer to the BMP RAM user guidance and other guidance videos for more information on determining the structural BMP type. MS4 and catchment name fields will automatically be assigned if this spatial data has been uploaded into your account. Feel free to contact Second Nature for more details if these fields do not appear in your account. A BMP can be saved in BMP RAM if location, unique name, and BMP type fields are populated. However, in order to assess BMP condition and track BMP RAM results, other information is needed. One of these is the land use type of the drainage area from which the respective BMP accepts runoff. Second Nature Stormwater Tools has reduced urban land use into 9 categories, 6 parcel types, and 4 road types. Parcel land uses include industrial, commercial, multifamily residential, single-family residential, cultivated, and other/open space. The road categories are high traffic, moderate traffic, low traffic roads, and unpaved roads. Select the land use category that best describes the drainage area being treated by the structural BMP. Multiple is a common case when inventorying a centralized BMP that is draining many acres consisting of a mix of land uses. The next step is to select the property ownership, either public or private, on which the BMP is located. Then, depending on BMP type, BMP RAM needs an estimate of either the total contributing drainage area to the BMP if it is a large centralized BMP, or the impervious drainage area if the BMP type is a smaller decentralized BMP, such as an infiltration feature or bioretention structure. Given that centralized structural BMPs are large-scale, costly capital investments, these systems require hydrologic analyses and civil engineer design plans prior to construction. Use of these documents will likely provide the most accurate determination of the total contributing drainage area of a centralized BMP. If these documents are not available, we recommend that after visiting the BMP in the field and marking its location, the user return to the office and evaluate the location of the respective BMP in the context of the urban drainage network. If users have completed the Second Nature urban catchment delineation efforts as defined in this document, available from our website, the location of the subject BMP relative to the urban drainage network can be inspected and the total contributing drainage area in acres can be quantified in the office using GIS or Google Earth. A combination of field inspections and office work may be necessary. The user should do their best to estimate the contributing drainage area of a centralized BMP to the closest acre. Decentralized structural BMPs have smaller capacities than centralized BMPs and thus treat much smaller drainage areas, likely no more than a couple of acres. Decentralized BMPs are sized based on 1. Selecting a specific rainfall intensity criterion like the 85th percentile storm event, and 2. Calculating the area of impervious surface on which the rainfall will fall before draining to the BMP. If the user is inventorying an existing decentralized BMP, like a catch basin or biofiltration unit, and no design information is available, it is recommended that the user identify the contributing area to the respective BMP in the field by walking the area and visualizing what areas would contribute runoff to the subject BMP. The user can use a hard copy Google Earth image or a mobile GPS application to drop a few location pins and designate the drainage area boundary. Once the area is reasonably delineated, the user can choose to return to the office and use Google Earth or another program to draw the area and obtain the acreage. The other option is to complete a reasonable field sketch of the area and use a survey tape or survey wheel to measure dimensions. When inventorying each structural BMP, you must inspect the perimeter of the BMP to determine the total number of inlets and outlets. The inlets convey water into the BMP, and outlets convey water away from the BMP. Outlets include both treatment and bypass structures. These values must be filled in, but they can be 0, like in the case of porous pavement, which has neither an inlet or an outlet, or an infiltration basin, which will have one or many inlets, but potentially no outlets at all. If the BMP is old and has not been maintained for a while, you may be required to climb through vegetation or infer that an inlet or outlet may be buried in material. make sure your designation of the number of inlets and outlets align with the type of BMP you are inspecting. Type-specific information is the next category for BMP inventory data. As seen in this matrix, the type-specific information are various fields about design and specifications, are different for each BMP type, and are mostly required for centralized BMPs. We're not going to go through all of these required specifications in this video, and we refer you to the user guidance document for more details. We select a few key parameters and provide tips on how to better generate these values in the field. With all of these, more precise and detailed information is better, but in some instances when no design information is available, you'll have to rely on the best available information to make reasonable estimates. Dry basins, wet basins, and treatment vaults are three common types of centralized BMPs. The schematics here illustrate how each of these BMPs is designed to treat stormwater. They also illustrate the required type-specific information, such as BMP footprint, treatment capacity, drawdown time, and treatment rate, that we want to collect for BMP RAM in order to understand the BMP's intended functionality. Our other user guidance materials go into more detail on how each of these BMPs works and how to properly identify them, and we encourage you to check out those videos for more context on some of these type-specific BMP inventory items. The type-specific information gathering can be initiated in the office if any designs or plans can be located and used for reference. If the BMP was recently constructed, there is a higher likelihood that design plans can be used to inform these inputs. When designs are not available, or if the BMP is visually impacted by excessive sedimentation, vegetation growth, or there's other evidence of lack of maintenance, a field-based determination of these input fields is critical, as BMP records and designs will likely no longer adequately describe the BMP. More appropriately, if a BMP is in need of maintenance, those maintenance actions should be taken prior to taking these measurements. Even in the case when design plans are located and used to inform the design values we're about to explain, we strongly recommend that users perform some reasonable verification of the field values obtained by doing some simple measurements in the field. The first task is to determine the BMP's footprint, or the surface area in square feet at the base of the BMP. This can be estimated as a two-dimensional area. Obtaining this value can range from being easy to hard. For dry basins and infiltration basins, the sides of the BMP may also have been designed to infiltrate stormwater and reduce pollutant loads. In those instances, you should include the surface area of the sidewalls that are frequently inundated in your determination of footprint area. Footprint area, recorded in square feet, can be approximated in the office using the Polygon Measure tool in Google Earth Pro, or a DEM analysis with the GIS software. It can also be simply estimated in the field with a survey tape and hand sketch, or it can be more precisely measured using tools such as a survey level Stadia rod and rangefinder, or a total station. The level of detail and accuracy is up to the user. We recommend preserving your significant figures to represent your confidence in the measurement technique used. For example, a full survey with a total station can yield surface area estimates likely accurate to the nearest plus or minus 1 square foot. However, simply taking 30 minutes to delineate and measure geometric shapes to estimate the footprint using the survey tape and sketch method may only be accurate to the nearest 10 square feet, but for a centralized BMP that has a footprint over 10,000 square feet, the expected precision of the sketch and tape method is more than adequate. Additionally, as footprints get smaller, they become easier to accurately measure by hand, and the simple method may still be able to provide plenty detailed site information. Again, BMP RAM user can choose whatever techniques with which they are most comfortable. Treatment capacity and wet pool capacity are three-dimensional measures of volume associated with the BMP. These volumes are determined by the relative elevations of the treatment orifice, if present, and the bypass outlet. These elevations should be specified in any design plans, but should certainly be verified in the field with a Stadia rod, as sedimentation and vegetative aggradation can dramatically change these values. As with the footprint, calculating treatment capacity and wet pool capacity volumes can be as detailed as you want to make them, and can be done using both office and field-based techniques. Conceptually, the objective is to determine the representative depth over the square foot area to get the cubic feet and represent the three-dimensional space. For example, in a treatment vault that is shaped like a cube, the footprint is simply multiplied by the depth from the base of the vault to the bypass outlet to get this volume. In an odd-shaped wet basin, this is a bit more complex, but just as with calculating footprint, simple tape and sketch methods can go a long way towards generating these measurements. Treatment rate, infiltration rate, and drawdown time are a bit more challenging and time-consuming to measure in the field. So if BMP-specific design or engineering plans are available with that information, it's best to use them. Otherwise, we provide options for either using available literature to approximate the values or field measurement techniques. Treatment rates for proprietary media filters and treatment vaults can be found from the manufacturer's literature or measured in the field by contacting the manufacturer to determine the appropriate measurement technique. Bed filter treatment rates can be researched based on the permeability of the media and then converted to CFS based on the footprint over which the filtration is occurring. Appropriate field measurements include permeability tests using infiltrometers, constant head permeometers, or similar tools in order to determine the average treatment over the filtration surface. Infiltrometer measurements are covered in the BMP RAM user guidance and in another video called BMP RAM Field Protocols Infiltrometer Observations. Information on infiltration rates for various media can be found from the NRCS soil survey or other published infiltration rates based on the substrate type placed at the base of the BMP. We recommend that when using this approach, you consider the depth up to 4 feet below the surface and use the lowest infiltration rate. In the field, appropriate field techniques include ring infiltrometers or constant head permeometers. Multiple measurements must be conducted to represent the rates across the entire infiltrating surface of the BMP. Infiltration rates can also be determined through high-resolution monitoring and the development of a site-specific water budget. Typically, BMPs are designed to have drawdown times between 48 and 60 hours. Drawdown time can be calculated based on the BMP treatment capacity and the outlet's flow rate. Theoretical flow rates can be determined using typical engineering equations based on orifice dimensions and design. In the field, drawdown time can be measured using a water truck and recording the time it takes for a specified water volume to be lost through the treatment orifice. Or flow rates through the orifice can be measured using various techniques such as bucket tests, current meter, flow sensor, or others. All of these field measurements are an investment of time, resources, and equipment to perform. The field measurements introduce some bit of sampling error also, and therefore relying on available literature can be acceptable for most BMPs when design documents are not available. Finally, the user is welcome to enter any additional notes in BMP RAM that may be pertinent to the BMP at hand, though this is not a required field. Once all required inventory fields are populated, click the Save Data button. As mentioned earlier, the BMP location, ID, and type is all that is necessary to inventory a BMP and see it on the map. However, until all necessary inventory fields explained above are populated, benchmark and threshold values cannot be entered and the BMP cannot be rammed. This brings us to the end of this guidance video. Please visit bmpram.com and secondnaturellc.com for more information about BMP RAM and our other stormwater assessment tools. BMP RAM was originally created in 2009 and is incorporated into the Lake Tahoe Clarity Crediting Program. Recent refinements have been developed in collaboration with the Central Coast Regional Water Quality Control Board and the Low Impact Development Initiative. We're extremely appreciative of the continued public agency encouragement and support. Good luck ramming, and be sure to check out our other instructional videos. Thanks a lot.